Hi, everybody.
Good afternoon, sir.
Good afternoon. Thank you for joining. In the last class, we saw arrays and lists and linked lists. And in the linked lists, we specifically saw singly linked list, which means our node points to the next node in one direction only, singly linked. And today we'll be looking at first, let's start with a quick revision of what we saw that time. Let my screen. Share screen. Okay, so this is what we saw. We have linked lists in which we have a node, and then for the node we know the value and the next. So our class node has got two kinds of entries or two variables. One is the data variable, or what is the value stored in that node, and other is the next node, the pointer to the next node. We call it as a pointer, but don't confuse it with the pointer of C++ language. So here, pointer simply means a reference, and it stores the head of the next, or the basically the class instance of the next node value, next node instance, basically. Okay, so and we looked at different operations. So when we define an abstract data type, we can say, let me draw, when we define an ADT, an abstract data type, then we will define what are the variables. And we are following a notation here. Let's say when we define a class, let's say singly linked list, in that we first say define underscore init underscore whatever, and here we define all the variables like self.data, self.node, or whatever are the variables, and then we define the functions. Like the functions here are access a value, add a new link, or search for something, search for some node value, or remove some node, etc., etc. So we can define all the functions. So this is an abstract data type where we define the variables and the functions on top of them, functions on that class. And then how we implement it, how we implement these functions, what kind of variables we define. So based on that, our function, our whole program will have some complexity, some time complexity, some memory requirements, etc. How efficient or how inefficient our code is will be defined at that level, at that stage. Okay, so that was it. And this is what we discussed last time, singly linked list. Anybody has any doubts here?
Hello, sir.
Yes.
Sir, can you explain call by value and call by reference a bit?
I will do that. Okay, well, in today's lecture, I want to discuss something else, but I'll come back to your question after some time.
Okay, sir.
Okay, I want to share my Jupyter notebook now. Where is my Jupyter notebook? Let me create a new notebook. Oh, we had a notebook last time which we were using. Share the notebook. Okay, so here we are. Last time we were using this notebook and we had defined a singly linked list. Yeah, and we defined the functions access, append, insert, etc. We did not define remove function. Can we define remove? I want to remove a particular node. It's ith node, let's say I want to remove. So how do I go about it? Let me come to my, I will first, let's discuss the algorithm and then we will discuss the implementation. This one, okay. So the problem is I have to remove the certain node. Let's say this is my data. I have here Hari, Kamal. Okay, I want to remove, let's say Kamal. So I want to say remove 0, 1, 2, the second node. This is what I want to remove. How will I go about it? How will I do this? So I have, what do I have? I have a pointer to head, right? Self.head, which points to this node. I have a pointer to the tail, which is self.tail, which points to the last node. And then from here, I can use next to go to the next and next node. So how will I remove a particular node? What are the steps involved? Number one, yeah.
Will point Ram to Sita.
Yes. So what is the algorithm?
Sir, move I minus 1 times.
Yes. For
And
first
then,
move. Okay, I can say access I minus 1th node. Okay. Yeah, and then
change the ith this node pointer to I plus 1th node pointer.
Okay, I minus 1th 1 dot next basically should point to I plus 1.
I minus 1, yeah, dot next.
And anything else?
No, that will be
Point the ith node pointer to null, like the Kamal's point.
Yeah, that's a good point here. What you are raising, you're saying that I should, or basically delete I, right? Delete the ith node. That's what you're saying, right? You're saying there's a
Yes, sir.
step which should have delete I minus 1. Okay, so what happens in these languages? Many times, or in most of the languages, there is something called automatic garbage collector. So whenever there is no variable in our program which is pointing to some memory area, then or some allocated memory, then that allocated memory is automatically deleted by the garbage collector. So it automatically deletes. For example, here, if Ram points to Sita and does not point to Kamal, then there is no way I can access Kamal, this memory space, right? So this allocated memory will be automatically deleted by the garbage collector. But yes, earlier, let's say earlier languages like C, C++, this kind of thing was done manually. So you can also manually do it, or else you can let the program automatically do it.
Okay, sir.
So this, you can add this step or you may not add this step, both are fine. Okay, now yeah, this does this program have any problem?
yes, sir. For head it will not work.
Huh?
For head it will not work.
For head, why will it not work? Because if I is head or I is 0, then I minus 1th node will not exist, right? So what should we do in that case? For head, that is I equal to 0, what will be the algorithm?
Head equal head dot next.
Yes, simply you have this pointer head, so just point it to head dot next. So head points to this one, and this dot next points to this one. So if I just say head equal to, head is assigned the new value, which is head dot next. That's it. Okay, what about the last tail? Will it work for the tail? For tail, I is equal to 0, 1, 2, 3. I equal to 3, for example, in this case. Will it work?
I think yes, sir. Because I plus 1 is already none, so
Yes.
I minus
Yeah.
1 dot next is null.
Yes, so it will work. Okay. So in this way, you should always check your code for the edge cases. These are the edge cases.
Sir, how is it going to work? Can you explain once again? For the tail.
Okay. So generally what you will do here is you will say I minus 1 dot next, right? So when you do I minus 1 is this one, I minus 1 dot next is this, and dot next is none. So you are basically saying I minus 1 dot next is equal to none, right?
Okay. Okay.
Because this thing will become equal to none. So you are assigning that value here. Okay, yeah, that's it. Thank you. So I will write the code now. Let me share the coding screen. Yeah, here we are. So remove. So what do we do here? If first of all, if I is the head node, basically I equal to 0, then what do we do? You said simply head equal to head dot next, right? So head is where? Head is here, self dot head. So my self dot head is simply pointing to self dot head dot next. That's it, right? And otherwise, if I is greater than 0, of course, if I is less than 0, then there is no point. If I is less than 0, then you say return and don't do anything. And else if I equal to 0, then do this. And otherwise, if I is greater than 0, then what you will do first, you will access the I minus 1th node. So for that, we have to use the access function. Okay, self dot a. So my current node is equal to self dot access I minus 1, right? And then I have to say my I minus 1 dot next. So node dot next, I will replace it with node dot next, right? That's it. And deletion part I'm not doing. So that's it. And any other case left? No. That's it. That's it. So this will remove. So after writing the code, it's always a good practice to check if I have written correctly. Oh, name node not defined. Okay, I have to start from the top. Okay, so this is the thing. Hari, Ram, Sita, Suraj. And now here, let me delete SLL dot remove what? Let's say 0, 1, 2. Let's remove Sita. And then I do SLL dot print all. Yes, it works. It works for Sita. Let me check if does it work for the last node now, the tail node. Yes, it works for the tail node also. Now let's check for the 0th node, which means the head node. Yeah, it works. That's it. So it works for all the edge cases, and to be more sure, I will say this does not do anything. Okay, fine, it works in general. Okay, yeah, that's it. So what is the complexity? I think you can do complexity analysis yourself. What is the complexity for remove function? What is the complexity? O, how much?
N.
O n, yes. Because okay, what is the worst case? The worst case is that when you are removing, when you are
removing the tail node.
removing the tail node, yes. Yes, that's the worst case. So if the chain is very long, then it will take long amount of time also because of this excess function. Okay, so that's it, I think.
Sir, here if I is less than 0, then return statement is executing twice, right? Won't this raise any error?
If I is less than 0, then
Two return statements are there, return and return. Both will
no,
be
after this statement, it will not go any further. It will just come out of this function.
but sir, this return is last return is outside of if else statement, right?
No, it is return will take it out of this whole function.
Okay.
This function will end. So therefore, this return will not be executed.
Okay.
Yeah. Okay. Thank you. So this was all about linked list and singly linked list. And doubly linked list is something very similar. You have not just next, but also you have previous. So you store the value of previous node, or you store the previous node also in this. Okay, so I will not go into doubly linked list details, but you can do it on your own. They are very similar. Let's go to the next topic for today. Let me check what is the topic now. Okay, just a quick comparison between singly linked lists and doubly linked lists. So singly linked lists have some advantage and some disadvantages, and doubly linked lists have some other advantages and disadvantages. So singly linked lists. So okay, tell me what are the advantages of singly linked list versus doubly linked list? SLL versus DLL. The singly linked list has or uses less memory, right? Why? Because this you don't have to save self.previous, right? And it has slightly faster implementation and simpler implementation. Oh, basically, it has simpler implementation in general, and it is faster for add, remove kind of operations, right? Because when you're adding a new node, then you don't have to fill values for next and previous, but only next. Whereas if you are using doubly linked list, then you have to right? You have to add values for both previous as well as next nodes. What are the disadvantages of SLL?
Reversing is unidirectional.
Yeah, cannot go backwards. For example, if you are in a current node and you want to go to the, let's say you're in the ith node, you want to go to I-1th node, then it is not possible in O1. You have to start from the head and again go to I-1. So the complexity will be more. Okay, these are some pros and cons. So if you require to go back a lot, then it is advisable that you use doubly linked list. But if your application does not require to go back that frequently, then you need not implement DLL. You can work with SLL only. Okay.
So what kind of applications does not require us to go back completely?
What kind of applications don't require us to go back? Yeah, we will see some use cases and some applications. In today's class itself, I will give you one practice problem.
Okay, sir.
Yeah. Let's say you have two lists. Okay, anyways, we will see more examples. Okay, now what we are going to study are stacks and queues. What is a stack? Let me go to my teaching window. Okay, so we are doing today stacks and queues. What is a stack first? Stack basically means it's a pile of some things, right? Let's say these are some entities. Let's say this is Hari, Ram, Sita, etc. And what? Okay, so what is the single unit? You can call it as a node or a plate or any item, right? So let me call it as you can call it a node also, no problem. And what does node have? Node has a value and node has a pointer. What kind of pointer we will see? So the stack is basically, it is putting all the nodes together, and these nodes have values and you have stack. Okay, and now what are the functions or operations possible on stack? One operation is when you put something on top of it. Let's say this is the base. So you cannot remove Hari directly. To remove Hari, you have to remove Sita, remove Ram, and then remove Hari. And if you're putting something new, some new entry, let's say Kamal or somebody, then you have to put it on top only. You cannot insert anywhere inside. You have to put it on top only. And when you are removing, you can remove from top only. This is insert at top. Right? Just like you have a pile of plates, you can put the plates one on top of other. You cannot remove something from the bottom. This type of a system is also called last in first out system. Last in first out, TIFO system. So last in means this plate came at the last, and when you are removing, you will remove it first. Last in, first out. And whereas this Hari, it was sitting there and it will keep sitting until the whole stack is first emptied. This is a LIFO system. And what we generally use a head to point to the top of this stack head. And once the head is basically you put things on top of the head and head will move to the next thing, the new thing, and you can remove things from the top, and then the head will move to the lower thing, the one immediately below. And when the head becomes none, this means the stack has become emptied. So this is how the stack works. So the operations which are possible are one is called push or insert, one is called pop or remove from the top. And the other is called peek. Peek is just to check the value of the topmost plate. Let's say if I say peek, then it will return Sita. The topmost, or the head value is Sita. That's it. So that is a stack. Stack is very useful. It can be very useful because you will see it later how stack can be very efficiently used to make some algorithms. Okay, now the question is, how do we implement stacks? So stacks can be implemented with the help of lists also. You can use a linked list to implement stack, or you can use a simple list, the Python list, to implement stacks. So in the Python, you can say some stack is an empty list, right? And then you can say stack dot append equal to, let's say, Hari. And then again stack dot append. So here append stands for push, right? Oops. There is no equal. There is no assignment operator here. It's function only. And when you want to remove something, you will say pop, stack dot pop. And this will return the value. Let's say if I say val is equal to stack dot pop, then my val will be equal to, this will contain Ram basically, and my stack will become simply Hari. And this val will become Ram. So this is how we do pop. To peek the value, you will simply say, I want to see the last value, stack minus 1. You can say print stack minus 1, or value is equal to stack minus 1. So basically this is how we implement a stack using Python list. You can implement it in more complicated ways or in more efficient ways. For example, with the help of linked lists, right? So you can define a class stack. And here you can define functions. Here you put self, etc. And here you will say my head is equal to self dot head is equal to something. And then you will define all the functions. Functions are like push, pop, peek. That's it. So in this way, you can define your own way of stacks. I mean, in your own way, you can define the stack. Yeah. Okay, this was the concept of a stack. And let's look at the complexity of the stack now. What is the complexity of different operations? What is the complexity of push?
1.
Okay, yes. So basically, you are just adding to the top. It doesn't matter what is the total length of the stack, just adding at the top. So complexity is 1. What about pop?
Still 1, sir.
1.
1. What about peek?
1.
1.
1. Yes. Now we can define some other functions which are generally not used. Let's say search. These functions are generally not used, but who stops you from defining them? Search for certain item. Let's say search for Sita. Well, it means I'm giving an example. So what will be the complexity of this?
O-N.
O-N, because Sita might be at the bottom. Another function can be defined like define remove, which means to remove any entry from in between at the ith location. Generally, it is not used. These two functions are not generally used, but still you can define a data structure like that. So tell me, what is this complexity of remove?
N.
again. Yeah, because you might be removing something at the bottom. So you have to first go to the bottom, and then you have to remove it and then move everything, right? Okay, so this is what is a stack. Next kind of data structure which we are looking at is something similar, but instead of removing from top, if I remove from bottom, which essentially means that you are implementing a queue. So what is a queue? Okay.
So may I ask a question?
Sure.
Sir, are the stacks different from Python lists? I mean, what is the need of stack?
Okay, stack is an abstract data type, and you can implement it using anything. You can implement it using lists, or you may implement it using a function of your own, right? Of an implementation of your own. But it's a very useful abstract data type because you will see it in upcoming lectures, how it can be very usefully exploited or used.
Thank you.
So your question is how it is different from list. The answer is list can be used to implement stack. Means the Python list can be used to implement stack. But in terms of ADT, a stack is a kind of list. So if I say ADT list, then ADT stack is a kind of list. But if you want to talk about Python list, then Python list can be used to implement the ADT stack.
Okay, sir. Thank you.
Sir, but a stack basically limits the functionalities of list, right?
Yeah, yes.
Why don't we use list in place of stack?
Okay, good question. So in certain some things, list may be inefficient, right? For example, you may not require so many functions, but you want speed. You don't want many functionalities. You want just these 3 functionalities, but you want these to be very fast. If you use Python list, it may be slow because it has so many other functionalities, and also it will require much more memory. But here you will require much lesser memory, much faster implementation, right?
Okay, sir.
So in those cases, you may require stack. And yeah. Python is a very slow language, although Python gives you everything ready-made. But the cost or the price you pay for it is that it becomes very slow. Because if you want just this many functionalities, and you have to use the entire list, which is a very heavy data structure, which has so many functionalities, but makes your program slow. So if you work with more lower level languages such as C, C++, etc., or even other languages, then you may implement these things on your own much faster. Okay, so let's come to queues now. So what is a queue? You have a queue, basically a person is standing here, another person is standing here, and the person can come in from back, and it leaves from the front. This is called a queue, right? So what are the data types present here? The data types are, what are the what are the variables in this here? The variable is the head and the tail, or it's also called the front and the rear. This is the front, and let's say there are many people standing here. Then this is the rear. And what are the operations you will do on this? The operations will be when you remove only from the front, right? So when you remove from the front. This is called dequeuing. and when you when some, so this DQ basically means remove from front. And this is called NQ. NQ means, just like you have NQ means to put something on in queue. Put in from rear. Right. And then there is another function possible, which is called, so DQ is a function and NQ is a function. Another function which is possible is just peek, as you had earlier, peek. So what peek does is it just tells you the value at front. Just tells the value at front. Peek. These are the three operations which are defined on the queue. Again, you can use lists to implement the queue. Okay, I think at this point I will also tell there is another implementation of queues available in Python. I forgot the exact name. I think oh yeah, I think it's called from collections. Import DQ. So DQ is another implementation of a queue in Python. And it gives you the function, many functions of queues are implemented here. I think it's a little bit more efficient than using lists. Okay, so anyways, you can implement it on your own also, because now you know how to implement linked lists, and that exercise is sufficient for you to implement any other list kind of data structure. Okay, let's look at the complexity. What is the complexity of NQ function? What is the complexity of NQ function?
1.
1.
This is O1. What about DQ?
1.
Again, it is
2.
Yeah, because you have the pointer front, right? So it's 1 only because of this pointer. Okay, what about peak?
Again 1, sir.
1.
Again 1, yes. And if you want to implement those functions like search and remove, then here again the complexity will be ON. Like you want to search something or you want to remove something from middle somewhere, then the complexity will be ON. Okay. Now, okay, there is another notion of priority queue. Let me describe that. What is a priority queue? Priority queue is a very useful concept. Okay. For example, imagine there is a queue. There are people standing here, but some people require immediate care, and some people may does not require that urgently the care, right? So there is an urgency index also here, or priority index. Let's say you want to attend the patients in the order of highest priority. So let's say the priority of this person is 10, priority of this person is 8, priority of this person is 5, priority of this person is 1. So now when you say DQ, then DQ will remove the person with the highest priority. So basically you have to make sure that your queue is always sorted. So this should be always sorted, always sorted on the priority index. So when you NQ something, when you add something to the queue, you have to enter not only the data, but also the priority index. You will enter not only the data, but also the priority index. For example, the new person comes, this person has got priority index of 11, then that person will directly reach here. It won't stop here, it will reach here. And then when you do DQ, this will give you the highest priority person, the data with the highest priority. Yeah, so that's the thing with the priority queue. Now, how do you implement a priority queue? Because here this is like a queue, but also you have to maintain the sorted order in the queue. So therefore, you use some quick sorting techniques, right? Like binary sort or bubble sort or things like that. So some sorting technique you have to use to keep the things sorted based on the priority index. And we will look at it. We will look at some sorting algorithms little later and some implementation of sorting algorithms little later in this course. But for now, yeah, that is the thing. You can use any inefficient sorting method also. Let's say if you're using lists, you can use some inefficient sorting method also here. I will just mention here. So we'll be looking at this later in the topic called heaps. When we'll study heaps, we will look at some efficient sorting methods. And then we will come back to priority queues, that how can we keep them sorted using heaps. Okay. Now, yeah, that's it. That's it for the queues and the stacks. Okay. Anybody has any questions here?
Sir,
Yes.
so can two entities have same priority? I mean, or do we need to remember the every priorities of every entity?
A good question. Yeah, yes, in general, two entities can have same priority, and then they will just stand side by side. Anything can come in front because they have same priorities. Any one of them will be in the front.
Okay, sir. Thank you.
Randomly.
Yeah, randomly means your algorithm maybe in the order of queuing or
Time of arrival.
pardon?
Time of arrival can be a
Time of arrival, yes. So depending on your implementation, if you are implementing it in a way that the person who comes later, it stands at the back. Yeah. But this ADT does not put any constraint on such cases. Your implementation can be either way. Yeah. So that's about queues. Do you have any questions until here? Okay. If not, then what I would like to do today is to solve a problem with you. So this was all about lists. Now the next topic will be something different. We will see some other topics in the next class. But today I will do one example with you where you will need the knowledge of lists. Or to be more particular, it is about linked lists. Let me define the problem first. Let me copy it. List. Okay. So first of all, I will define something and go to the I define a class node, right? The node, this is a singly linked list node, which only points in one direction, right? Now, this is how I define my list node. Now my problem is this. I have to define a function called merge two lists. And if I give L1, which is the head of the first list node, first list, L2 is the head of the second list, and I want to return a list which basically which is basically a merged list. It has got both the lists merged together, but both the lists are sorted. So the two lists are sorted. What do I say here? Merge two lists. L1 and L2 are sorted singly. Merge them to return a sorted list, right? So whatever you are returning, it should also be a sorted list. So I will draw here an example. Let's say your list is 1, 2, 5. This is your L1, basically the list 1. L1 points to this, right? L1 points to this. The L1 points to the node only, and then this node is a connected list. And other list could be 1, 5, 9. My L2 points to this one, right? Now you have to return a list which will be 1, 1, 2, 5, 5, 9, and this will be your L out. This is what you have to return. So how will you do it efficiently? That's the question.
Sir, we will compare the first element left in both the lists, and the smaller one will be put in the L out.
Yeah, we'll put the first element.
We will compare the remaining first element of both the lists, and the smaller one will be put in the L out.
Yes, yes. And then
Just this.
that is correct. The comparison has to be done, and based on the comparison, I will put the value in L out, and then
So the L out can be a stack, I think.
okay. So generally, when okay, the algorithm requires that my output should also be a list node only. So you have to implement it yourself. You can't use arrays.
Taking head of L2 and comparing it with every element of L1.
Take the head of L2 and compare it with the head of L1.
Yeah. And then
And whichever is smaller,
yes, yes.
that will go to L out, and then
moving that head of L2 to the next one, like 5. And then
okay. Let us write down the code for this. I will just share my programming screen with you. Mm.
Sir, do this list only contains numbers?
It can contain any, basically whatever is there, it is comparable. These are comparable items.
Like if you are doing the sorting, then it should be number only.
Yeah, yes. So
So-
it can be either numbers or characters. Characters are also comparable. Numbers are also comparable. And if you are using strings, then you have to define a notion of comparison there also.
Okay.
So whatever is there, they are basically comparable, and you can use less than, greater than sign to compare them. Okay, let me share the screen, the program screen with you. Okay, this is the question. So in case you want to practice more problems, there is a website called leadcode.com, and I took this problem from there. This is a very good, it has got many interesting problems. You can visit this for practice. Okay, so tell me now, let us write the solution. So in general, I would like to do these test cases. Whenever I write a code, I should test my code properly, that it is giving proper results for general cases as well as for edge cases. And this is what I would like to check finally. Okay, let's first write the code. Yeah. Yes. How should I start?
Sir, do we need to output a new list, or I can like start inserting the elements of L2 into L1?
Yeah, you can do that as well.
So, sir, we'll start from
Yeah,
head of
ultimately, see, one thing you have to note here is that you don't have any list thing here. It's just a connected units. Units are there. You can connect them in any way you want. Instead of creating new nodes, you can just reconnect them in a way that they are the merged list, right? That way you'll be saving space also.
Yes.
And you have to return just the head node, and everything else is automatically accessible via the next keyword. Okay. Okay, first what I would like to do is I will let me write down this is some basic things I have to do. First, let's create an instance of this solution class, right? Because I want to access sol.merge to lists. Okay. L1, L2. But what is L1, L2? Let's define that. So my list 1 is, let's say, 1, 2, 5, and list 2 is 1, 3, 5. But the thing is, I have to convert them into linked lists first, right? So let's define a function called list2chain. I'm just calling it as chain, but okay. List2chain. List 1. Let's define the function. Define list2chain, and I give a list here L, let's say. So what I would like to do here is, let me make a head node. Head is equal to list node something. List node. Okay, here is a very nice trick which I learned from another person. Oh, this is something interesting. I can create the head as just a dummy head, right? Just a dummy head. And I will say then current node is equal to head start with, and then I will traverse the length of this L. I will say for value in list L, right? Current node dot next is equal to list node val. Right? Basically, what I'm doing is I'm creating a new node with the value val, which is basically from this list, right? This list is, let's say 1, 2, 3, 4, 5. Then this value will be first 1, then 2, like that. So I'm just creating a new node in this way. And then current node dot, and I move to the next node basically. Current node equal to current node dot next. In this way, I will keep doing it until all the values are exhausted. And now here, see the trick. Now remember my first element or my first node was just a dummy node. So I will not return head, I will return head dot next. Right? Did you get this trick? So let's not do this. Oh, I need a method to also print the whole chain. So let's write a method to print the whole chain here. I will say print chain, okay. And you give me the head here. Or just basically a node, which head is also a node, right? Define, so head node. Now I will say while node is not none, simply print node dot val. I think this we have already done it, in the last class. So I'm doing it fast. End equal to a comma, right? And node equal to node dot next. That's it. So here I have reached here. Now I want to print L1. Oh, no problem. I did some mistake somewhere. List to chain. Oh, I don't have to print L1, but I have to print L1 dot value, right? No, sorry, it's print chain. What am I doing? It's print chain L1. Yeah, now it's correct. 1 to 5. Yeah, that was L1, 1 to 5, right? And let's check this one. If it is an empty one, then yeah, it prints nothing. Yeah, so fine, this works. Okay, so I have created the chains now. L1 is the list node and L2 is also a list node. Let's do that. Okay, now we are ready to tackle our problem. Now I will say L out is this, and I will say print chain L out. Yeah, so now how do we implement this function? First, think of an algorithm, and then let's implement it. Should we go to our writing pad to think of an algorithm? Yeah. So let's start from here. I don't have allout, so let me define an allout. So my allout points to some dummy head, let's say -1 or something, some dummy head. And my L1 points to this. Okay, my L2 points to this, and my L1 points to this. And these are the variables which I have access to. Right? I have access to these three variables only. And using these three variables, I will access my data. Tell me now, what is the algorithm? So I have initialized my allout, right? Initialize allout equal to basically a dummy node. Okay, then what next?
Compare L1 and L2.
Compare L1, L2. Okay, then should I put a if condition?
L1
If
is greater than L2.
L1 dot value is less than L2, less than or equal to L2 dot value, then
allout dot next is equal to L1.
allout dot next equal to L1. Yes.
And L1 equal L1 dot next.
L1 equal L1 dot next.
Else
Else
allout dot next equal L2.
allout dot next
Equal
to
L2.
L2.
And L2 equals L2 dot next.
Very good. Yes. So essentially, let's do an iteration and dry run with this example. Dry run means just our manually with our hand we do the implementation of the algorithm. So L1 dot value, both are same. So this condition will be met because equality will be met, and my allout dot next will become equal to L1. So my allout dot next will be L1, which means this will point to this one. The next will point to this one. And then you have said L1 equal to L1 dot next. L1 is assigned the value L1 dot next. So basically this connection will be broken, and this connection will rather go to this one. Right? This is our new situation. Then what next? That's it. You've done just one step. What about the next steps?
We have to loop it.
Yeah. What kind of loop you want to put?
While.
While loop. Okay. While. Okay. While. What condition? Let me. Can put while loop easily now. Yeah, while. Yes.
L1 is none and L2 is none.
L1 is none and L2 is none.
L2 is none.
Is none or is not none?
Is not none. Is not none.
Okay.
And sir, in comparison, we should use allout dot val. Allout dot val should be compared with L1 or L2.
Allout dot val should be compared with
L1 dot val once and then L2 dot val.
two comparisons. No, see, your L1 and L2 were already sorted. So once you have taken your allout as this one, then you know this value will always be greater than this, right? This L1 dot val is always greater than allout dot val in this case. And if it were the other case, let's say your L-out would have been L2, then your L2, the new L2 dot val will be greater than or equal to always L-out dot val. That you already know because the lists were sorted. Right?
Yes, sir. Yes.
So therefore, this is sufficient. Okay.
Sir,
Yeah.
in the while loop, doesn't the and should be or? If
Should be or this, but that will mean that if L1 becomes none and L2 is not none, then your loop will keep running. Do you want that? If your L2 becomes none, then this will give an error, right? L2 dot val, none dot val will become an error. So and condition is fine here. Okay. What next? Okay, so then this will keep running. Okay, then this will, let's do this, the next iteration. Now here, you have to compare L1 and L2. So when you compare these values, then you will see this one is smaller. So what will happen is this L-out, which points here now. Oh, no, L-out is not updated. L-out is not updated. When you do the second iteration, then your L-out will simply move to this one. Your L-out will move to this one. But you don't want to change your L-out. You want to change your L-out dot next. You basically, this pointer will go away from there and will connect to this one. Then it will go away from here, it will point to this one. So basically you are losing, you're not saving the information. Are you getting it?
Yes, sir.
Yes, sir.
What is the problem and how will you rectify this problem?
So we should be updating allout.val and then allout.next should be a new node.
Okay, tell me how to do it.
So the while is correct and then the if condition is also correct. So the next line should be allout.val equal to L1.val.
Sir, simply allout equal L2, allout dot next will suffice, I guess. Adding this.
Here you say, but then what will you return? You want to keep a hold on the starting node, the head node. Otherwise, what will you return? You want to keep a variable always pointing to the head node. So basically you have to define two variables here. One is the head allout and the other is the current value. Right? Let us call it as allout head. I will define another variable called allout underscore head, which finally I will return, right? I want to return the head. Right? Now you can update your allout, no problem, because allout.head can be used to access the first node. So I will say allout underscore head equal to allout. Right? Now you can update your allout. Now you will say allout equal to allout dot next, right? That's what you are saying.
Yes. In both conditions.
Huh?
Okay, yeah, fine.
In both the conditions. So basically now what happens is when you do this comparison, your allout will point to the, your allout won't point here. Allout will point to the next node. Your allout now points to this one. This connection is anyways there because of this dot next. And but allout points to this one. And then what next? Again, when the next loop will run, Then L1 and L2 are compared. This one is smaller. So now allout. So first you will make the connection that allout dot next is L1. So this connection is made first, right? And then you will make the, then you will move the allout to the next node. The allout will move to the this node. And then your L2 will also be pointing to the next node, right? So this L2 will now point to this node. Yes, now again you will do the comparison between L1 and L2. This one is smaller, so you will make a connection from here to here, and you will move your allout to the next node, which is here. Then again you will move L1 to the next node. This one goes away. Right, now again you will compare L1 and L2, and both are same. So I think L1 will update it. L1 is updated. So you will move, now you'll make this connection. This connection comes. This connection was broken. I had broken this connection. This connection comes. This connection was also broken. That's why this went here. Now, yeah, and L1 will be updated. L1 will point to none, basically. L1 becomes none. Yes, so what will you do next? And your allout is also updated. So now if you compare, now L1 is now the loop is broken. Now the loop has ended. What will you happen? What will you do now? Still there are two nodes in L2 remaining. L1 is none, L2 points to this one, and allout is this.
Simply connect the L2 to the L1 node, which is the 5 of the L1.
Okay, so after this loop is broken, after this loop finishes, then you will do what? You will say, yeah, allout dot next equal to L2, right? Right?
Yes, sir.
Basically, this is the case. If, just a moment. Oh, what has, so if L1 is none, and if L2 is none, then do the other thing. Right?
Yes, sir.
Yeah, and will that complete your algorithm? So basically, okay, now L1 has become none. So what you will do, you will say simply my allout will become L2. No, this is not correct. Oh, L2, allout dot next equal to L2. Yeah, allout dot next. Basically, I make this connection. Allout dot next, instead of going to none, it will go to now here. And my allout can vanish now. I don't need my allout anymore. That's it, right? It's done. That's done, right?
Yep.
Because this is anyways complete. So we can end our algorithm. Then we can what we will return now?
Allout
Return what?
head.
Allout head. Very good. That's it. So you have completed your algorithm. Let's write it here in our program. I'm just copying things from our here. Let's start here. So first you have to initialize the allout equal to list node, just any empty value basically. And then when you're returning, you will be returning allout underscore head dot next, right? Because the first node is the dummy node and I don't want to return that. So, and allout underscore head equal to allout. Right. And now we have to put the while loop. While L1 is not none and L2 is not none. I have to say if L1 dot val is less than equal to L2 dot val, then allout dot next L1 and L1 equal to L1 dot next. I'm just copying whatever you wrote on the writing pad. Else allout dot next equal to L2 and L2 equal to L2 dot next. I'm calling it as equal to, but actually it is assignment operator. So allout is assigned as allout dot next. Okay, and then once this is over, then you will say if L1 is none, then allout next equal or is assigned as L2. Else, basically if L1 is not none, then L2 will be none because otherwise this loop would not have terminated.
So allow dot next.
Oh, sorry. Allow dot next. Thank you. Equal L1. That's it. And then return allout head dot next. Yeah, this is important that the first node was a dummy node. Don't return that, but return the next one. Okay, so should we test it now?
Yes, sir.
Okay, all set for testing. Let's see the result. It should print the, oh, it printed the right value. Okay, let's see. So 1 to 5, 135 becomes 1, 1, 2, 3, 5, 5. This is correct answer, right? Let's take the edge case now. When list 1 is empty, list 2 is 2. Let's make this as empty, basically. Let's check. Oh, it is able to handle it without any error. Wow, no problem. That's very graceful. No error. Yeah, no error. Okay, what about when both are none? No error. Yeah, so your algorithm passes the 3 test cases which we made. It's able to pass all 3 test cases. So congratulations, it's done. Yeah, no error. Okay, anybody has any questions at this point? So the problem is solved. Okay, if there are no questions, then we can stop here. We will meet again next time on Tuesday, 2 o'clock.
Sir, call by value, call by reference, you told that you explain a bit.
Okay. There was a question in the beginning. What is call by value and call by reference? Let's take it up. You remind me in the beginning of the next class. I will definitely discuss this Call
Okay,
by
sir.
value and call by reference.
Okay, sir.
Okay, thank you.